Good morning, afternoon, or evening, everybody, wherever you are. Uh, and thanks for inviting me to present this my topic, hallucinations in ASR systems. Let me begin by introducing myself. I am Bhiksha Raj. That's what I look like when no one's looking. I'm a professor in Carnegie Mellon University in the Language Technologies Institute. My research areas include speech processing primarily, but generally computer audition, privacy and security, and deep learning. So the topic of the day is hallucinations, and hallucinations have always been associated with humans. They are a symptom of psychotic disorders in humans, which are mental illnesses characterized by a loss of contact with reality. So they are false sensory perceptions that occur in the absence of actual external stimulus. And like these really intelligent human systems, artificial intelligence systems too do hallucinate, large language models in particular. In LLMs, hallucination refers to the generation of text that appears fluent and coherent, but it's factually inaccurate and, more importantly, cannot be grounded to real world information. It's just been generated de novo for some odd reason. So, what about ASR systems? Can they also hallucinate? It turns out they too can hallucinate. And we have sort of in the research field has cataloged a variety of different types of ASR hallucinations. I have a few examples here. And this table, let me play out a file if you guys can hear it. Can you hear that at all? I
Yes, I
suppose.
could hear it.
Okay.
Yeah.
Yes. No. Okay. I didn't share the audio. That's the fault. But what the person really says is for the 1 hour and 7 minutes, and the ASR system came up with their main ingredient is sunny. The second one is no meteor down the chimney, and the ASR system comes up with you broke cats. What are your names? Or whisper tiny looks at an empty segment and thinks it says, I'm going to put some water on the bottom of the pot. So in all of these examples, the sentence on the right looks pretty cogent. It just has absolutely nothing to do with what was actually spoken. And in fact, nothing may have been spoken at all. So these are hallucinations. But then what's new? How are these different from the generic kind of errors that ASR systems make? ASR systems have been around for a very long time, and since the 1950s, and they've always made errors. Here is this infamous plot by that Dave Pallet showed in the 1998 DARPA evaluation workshop, where he shows how these SOTA speech recognition systems perform on various tasks. On each task, the error rate starts off high, and as the SOTA progresses, the error goes down, at which point we jump to a more complex task. The point is not this chart. The point is that ASR systems have always made all kinds of crazy errors. When did they go from just making errors to hallucinating? What is the difference? So, for this, we have to look at the kinds of technologies that we use for ASR systems. The legacy systems are all HMM based. More recently, we've used CTC based connectionist temporal classification based systems. And the most recent systems are all transformer based systems, which could be encoder decoder or decoder only. In HMM based systems, the units of speech, namely the phonemes or the words, are modeled by HMMs. The entire language is modeled by a giant HMM, a graph against which the incoming speech is aligned. And the path of best alignment gives us the decode, our best guess for what was spoken. In this process, every segment, every frame of the input speech is forced to align against some portion of the hypothesized output. So this makes it impossible to hypothesize long strings of words without input. And this is the hallmark of hallucination. So also the more recent CTC systems, they are similar to HMM-based recognizers in that the input is time-aligned to the hypothesized output. And so the errors, once again, are similar. And what do these errors look like? ASR errors typically include deletions, where we may not recognize a word that was spoken, or insertions, where the system hypothesizes a word where there was none, or substitutions, where it replaces one word with another. But in every single case, the hypothesized word sequence was time aligned to the input. Now, the errors can be pretty bad. Here is a really poor model that we trained many years ago just to illustrate how bad the errors can get. Here, what was actually spoken was this: as competition in the mutual fund business grows increasingly intense, blah, blah, blah. The recognizes output as concatenation. I can't even read this. But if you try to read this carefully, you will find that it's phonetically plausible given what was spoken. So there's phonetic grounding in the audio. This is not something we'd call hallucination because it can be related to the audio. Here's another example. The hypothesis and the speech were completely have no relationship. The actual word sequence was he spoke about a new legislative bill. The recognizer says ha 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 ha. But then this output is time aligned to the audio. So although it looks like a hallucination, it's the recognizer cottoned on to some background noise, and there is some grounding in the manner in which the output was generated. So these two, it's very questionable whether we can call this a hallucination. When we speak of hallucinations, there can be no phonetic grounding. The output is not phonetically related to what was spoken. It's not semantically related to what was spoken. It need not even be temporally grounded. In fact, there may be no input at all. So the classic HMM-based systems and CTC-based systems, which force alignment between the hypothesis and what was spoken, they can't hallucinate. For that, we need transformer-based systems, which could be encoder-decoder or decoder-only systems. Now, in transformers, the input is processed by an encoder, which generates a sequence of features, and then the decoder operates on this in an auto-regressive manner to generate this spoken sentence. And weak or missing audio causes the decoder to fall back on linguistic priors, which means the decoder can generate outputs when there's no audio at all. There is no grounding on the audio. And so what comes out can be completely unrelated to what was actually spoken. And so you end up with hallucinations. So we have a definition, but how do we evaluate these? To evaluate these, we need to be able to detect that a hallucination has happened. We need to be able to categorize them, and we need to quantify the occurrence. So it turns out there's been a ton of work on this, but at the end of the day, there's no error taxonomy, there's no context-aware labeling, and there's no way to distinguish hallucination versus phonetic or oscillatory errors. There's no analysis against model types, scales, or domain shifts. Threshold-based metrics, where they try to attach a score to it and compare it to a threshold, don't really work. So we come up with our own method, which is LLM-based, where we introduced a metric called the hallucination error rate. And the entire thing is obtained using just a large language model, GPT-4o in our case, where it classifies the outputs into different categories, whether it's a hallucination, or whether it's a phonetic error, an oscillatory error, a language error, or whether there's no error at all. And the short story is, our mechanism aligns very strongly with human annotations. The agreement between our method and humans is as good as the agreement between two independent human annotators of the speech. So how do we do it? We actually use an LLM and give it a prompt and ask it to categorize the sentence that was recognized, providing also the ground truth. And in the coarse-grained version, we say, tell me if this is a hallucination error, non-hallucination, or if there's no error at all. And the fine-grained version, there are more categories. Is this hallucination? Is it a language error? Is it an oscillation error, a phonetic error, or no error? And what does the actual process look like? I won't actually go through this, but we give it a very detailed prompt and several examples. And then, along with this, we provide the recognizer's output and the ground truth. And we tell it how to categorize the output. It turns out it can do a job that's at least as good as a human being. Taking that as a given, now can we quantify hallucinations? To do so, first we need to perturb the speech. So we start off with some nice speech and perturb it in different ways. In one case, we disturb the distribution shift of the test data from what the model was trained on. In the other case, we add synthetic perturbations, including adversarial noise, and we measure these degradations. We analyze the influence of architecture, model size, supervision, and so on to reveal systematic failure modes. We need an error metric. We define something called a hallucination error rate. The HER is the fraction of recognition errors that can be categorized as hallucinations. And so the way this is defined It's possible to have 100% word error rate with 0% hallucination. It's also possible to have a very low word error rate, like 1%, with 100% hallucination. A word error rate degradation is how much the word error rate degrades when we introduce a new influence like a domain shift. A hallucination error degradation is how much the HER degrades when we introduced a perturbation in the data. And so here are some results. This is where we shift the domain distribution of the data. We can quantify it in terms of the distance between the embedding means of the training and test data. And we have plotted both the hallucination error rate degradation, shown in green here and in the green plot, and the word error rate degradation for different models. And what we find is that these two track very closely. But interestingly, you can have very high hallucinations when the word error rate is small, and you can have high word error rate while the hallucination is small. So comparing it to model size, we find that as the models get larger and larger, both the hallucination error rate and word error rate go down. But they keep flipping, meaning you can have low word errors and high hallucination errors, and vice versa. I have a big chart here of a large number of tests we perform. I'll skip these and skip the next slide as well, and just gloss over it, where we show comparative results of hallucination errors versus word errors. The two tend to track each other, but there are situations where the word error rate is high and the hallucination error is very small, and the others where the two are pretty close to one another. So the upshot of this is that low hallucination rates can be marked by high word error rates, and dangerous hallucinations can be masked by low word error rates. Adversarial perturbations, which are becoming increasingly prevalent, have a greater impact on hallucinations. And hallucination is most strongly correlated with domain shifts, where the test data domain is significantly different from the training data domain. So, of course, once you have defined these things, we know these happen. We need ways of detecting and mitigating them. There's a lot of literature on it. I created a table. Obviously, I'm not going to have results time to go over all of this. But the point of it is none of these address the problem fully because we do not have a proper ontology for hallucinations yet. So in closing, we sort of briefly looked at the relation of cognitive phenomena of hallucination to hallucination in AI, specifically ASR, and defined what we mean by hallucination in ASR. I had some extra slides which I couldn't speak of. I was discussing causes, but we did look at the quantification. What we need, the need of the hour, is mitigation strategies and proper benchmarking. We've released a benchmark from my group, but it turns out that the field is still woefully behind in dealing with this problem. I'll stop right here and thank you all for your time.